Hi, my name is Bharatwaj Palvanan. I'm an assistant professor in the mathematics department at IISc Bangalore. In this course, we'll start by studying integral extensions, and then we'll move on to valuation rings, paying particular attention to discrete valuation rings and periodic integers. After that, we'll study Dedekind domains and the factorization of ideals there. And again, we'll pay special attention to Galois extensions. We'll end the course by studying the class group. If you're tuning into this course, you must have taken a first course in abstract algebra. You've seen the definitions of groups, rings, and fields, but you must still be wondering how to apply these abstract concepts to research in number theory. For many of us, the fascination with number theory comes from something very simple, solving Diophantine problems. Can x to the n plus y to the n equals z to the n have positive integer solutions when the exponent n is larger than or equal to 3? This is Fermat's last theorem. Which positive integers occurs as the area of a right triangle with rational sides? This is the congruent number problem. For those of us studying in India, there is another source of inspiration. Srinivasa Ramanujan worked on conjectures, identities, objects that he understood purely through intuition. When mathematicians eventually caught up, they discovered that he was working with some of the deepest objects in number theory. Here's an open secret. Modern number theory is not about finding solutions to isolated equations. It's about finding hidden connections between objects that on the surface have no business being related to each other. I think of number theory as a vast ocean with many rivers flowing into it. The resolution of Fermat's last theorem, for instance, I view it as being resolved because the river of geometry flows into it through this theory of elliptic curves. The work of Ramanujan led number theorists to modular forms, and we can think of this as the river of complex analysis flowing into number theory. Remember the congruent number problem about the area of a right triangle with rational sides? It's secretly a problem about elliptic curves. And the only tool we have to tackling this question is the Birch-Swinnerton-Dyer conjecture. It's one of the greatest unsolved problems of our time, and it's a millennium prize problem. But here's the thing, the Birch-Swinnerton-Dyer conjecture itself is part of a family of conjectures called the Bloch-Kato conjectures. These sweeping conjectures all share the same mathematical DNA, and the baby case that you have to master first is a classical theorem called the analytic class number formula, and at the heart of that formula is an algebraic object called the class group. The main focus of our course will be the class group, and we want to develop the commutative algebra to understand the class group properly. The title of the course, Commutative Algebra with a Viewpoint Towards Number Theory, is actually inspired by David Eisenbach's book, Commutative Algebra with a View Towards Algebraic Geometry, and that's our goal, to understand arithmetic through algebra. I invite you to join me on this course, Commutative Algebra with a Viewpoint Towards Algebraic Number Theory. Enroll on NPTEL, and let's begin our journey. Thank you.